This extra credit Zoom session is being brought to you by the Fractal Globe Snow Wheel Black. All right, so for today, go over this inverse trig functions, which of course we covered in the book itself. Here is more of the same. Okay, the inverse trig function. The arc sine, written sine inverse, also written arc sine. Y is arc sine x if sine of y equals x. Graph looks like a piece of the sine wave flipped sideways, so it's marching, going up and down the y-axis rather than the x-axis. If we have a distance y, in this case negative, moved along the y-axis, and we extend it to the right half of the unit circle, in this angle, y is the arc sine. Sine of the arc sine is x, basically any x. Arc sine of sine x equals x for x in the range, from negative pi halves to pi halves. For x outside that range, it doesn't quite work like that. It looks like a sawtooth wave. All right, now a triangular wave. Y equals arc cosine, written this way. Cos y equals x. Here we go over distance x, in this case negative, along the x-axis. Draw a vertical line, and where it meets the upper half of the circle, this angle is the arc cosine. So arc cosine goes from 0 to pi radians. Its graph looks like this. Arctan, tan inverse x, if tan y equals x. Here we go up and down along this axis, so along this vertical line, x, in this case negative. And we draw the radius out to the center. And where it meets the right half of the circle, between minus pi halves and pi halves radians, this angle is the arctangent. Its graph looks like this, which looks like the part of the tan graph on its side. Next. There's some basic rules about sine of arc sines and so on. Cosine of an arc sine. If we have a distance x here and a distance 1 along the hypotenuse, then by Pythagoras, this distance is root 1 minus x squared, and this is arc sine of x. So cosine of arc sine is this over this, root 1 minus x squared. Tangent of arc sine is x over root 1 minus x squared. Here we have sine and tangent of arc cosine. So if we go over distance x adjacent, and here's a radius, here's a hypotenuse of 1, and the second side by Pythagoras is root 1 minus x squared, and this is the arc cosine of x. Then sine of arc cosine is the opposite over hypotenuse, root 1 minus x squared. Tangent is opposite over adjacent, root 1 minus x squared over x. Now we have sine and cosine of arctan. So we have opposite is x, adjacent is 1, so this angle is arctan x. And this hypotenuse is root 1 plus x squared by Pythagoras. So sine of arctan is opposite over hypotenuse, x over root 1 plus x squared. Cosine of arctangent is adjacent over hypotenuse, 1 over root 1 plus x squared. Now here's the thing about how to evaluate solid equations. Sine of x equals a for what x? All right, well, there's this value here, which is arc sine a. Then you can go up 2 pi n, 4 pi n, 6 pi n, minus 2 pi n, and so on. So there's a family of solutions. Arc sine of a plus 2 pi n. There's also this solution here. And if this is 0 and this is pi, this is back the same distance, this is forward. So this is at pi minus arc sine a. And again, so pi minus arc sine a. And again, we add multiples of a full rotation. So those are the solutions of arc sine x equals a. Cos x equals a has these solutions. This is arc cosine a, this is minus arc cosine a, and then again, we add and subtract multiples of 2 pi. And to solve tan x equals a, well, here's a tangent function, here's x y equals a. Solutions are here. This one is at arctan a, and then it's move up or down multiples of pi. So arctan a plus pi. All right. And okay, so the extra credit set has these. Given these sides, what's alpha, what's beta, what's b, what's alpha, what's beta, what's c, what's alpha, what's beta, what's a. Here I ask for cos of arcsine, tan of arcsine, so do the same stuff on the second page. And I ask for exact values. So don't give a, I mean, I'm sure they could give you a decimal value, but I want to have something where we say we want exact values, fractions, exact fraction values of all these. 7, 8, and 9. Here I want to have arc sines or arc whatever of a half and so on. And so I want to have the exact either in radians or degrees. And also there'll be plus or minus 2 pi n or plus or minus pi n in all these. This one, ditto, I want exact values. Okay, well, that's it really for this. Let's see what comes after that. I'll discuss that next time on Monday. The stereo vision extra credit set, given a angle alpha here and angle beta here and a distance c between these 2 points. What's A, what's B, what's D? If these are your 2 eyes and these are the angles your eyes are pointed in at something, and C is the distance between your eyes, and A, B, and D is the distance to the object, and that roughly is how how stereo vision works. So evidently you use trigonometry in your nervous system. And I get a formula for it and I ask you to solve it. That's for next time. Well, okay, like I say, it's been now that we're off the edge of the book, all I'm doing is basically holding office hours and briefly going over extra credit sets. Questions, comments, suggestions, requests?
Do you think you go over your fractals at any point in any sort of detail? I think a lot of them are really cool. I'd be interested to see you make one or just see how the process works for you.
Show you how it does it. I use them. I make them using a Xerox machine. Everybody says they look like they're made by computer, but no.
Yeah.
No, they're not. Okay.
Huh. That's even more fascinating.
Let me find one which is here's a okay, this is Horizon, one of the first ones I made. I start off by making this by pencil and paper. Okay, pencil, paper, compass, and marker. Okay.
Mm-hmm.
And I made 2 copies of this, reduced to 50%. Here and here. And I cut and paste them into this.
Wow.
And then I made 2 copies of this, cut and paste them into a bigger copy. 2 copies of this, here they are, cut and paste them into a bigger copy, and so on until it basically converged. You know, obviously this is only finally many levels deep, so it's not infinite depth but it's close enough to fool your eye.
Sure.
So there that is. And yeah, there's just a whole bunch of them over the years. I just started making them, good Lord, in 1980s. Good Lord, and I've been doing it every so often ever since.
Well, that's really cool.
And
a lot of it reminds me a lot of the Tool art lately, of the band Tool. They do a lot of similar stuff. Fractals and things. Oh, not quite what you're doing, but you know.
Mine is, I gotta admit that mine is very mathematical, rather rigid. Nowadays, computers do these really gnarly, smooth looking fractals. I can't do that. If it's a Xerox machine, then straight lines remain straight lines. But so it makes it more crystalline and so on. But
yeah.
So I mean, let's see. There'd be things like tripod snow star or this. I mean, sometimes they surprise me.
Yeah, do they morph and change as you go, and do they spurn probably new ideas too, right, of things you could do?
I mean, you notice that this one, you can't see the triangles as well. It's kind of wobbly, whereas with these, you can see them quite plainly, and that's strictly an accident because here these kind of Y-shaped things are pointing down, whereas here they're pointing up. So somehow that obscures the line and makes it more fizzy and wobbly, whereas with these, it gets out of the way of the line, and so you can see it quite plainly. So it's not particularly trigonometric. I mean, sometimes I have to pick up the exact proportions. They have to make the subcircles and subsquares made of. For example, the inner thing is to these ones. These are to the big ones, and I have to use a rate. This is in a ratio of, I think, square root of 2 minus 1, so 0.4. And that makes it fit together. And I had to do it. And I had to, I calculated it. And, okay, I used the calculator. I used my.
That's okay. Yeah, they're really cool. They're really interesting. Have you ever done any solids, like the sacred solids, the dodecahedrons, or anything like that?
No, you can't do it.
Yeah.
Yeah. Although, I suppose you could, in theory, if you had a 3D printer, make a Menger sponge or something like that and have it printed out. Wait, that's too rich for my taste.
Yeah.
So,
a lot of beautiful art in there. It's impressive to see.
It's I am truly amazed. I mean, like I say, there have been times I would sit there, I just sort of look at it, I go inward, and I go outward, I go in, try and see it as a whole, try and see.
Yeah.
Oh my goodness. So this is Black Rose. Oh my God, this is certainly looks like a stained glass window. It's Rulo Supinski.
Some of them even actually look like they have movement, but obviously they're just static images. It's impressive.
I see your point. You go in, you go out, and your eye can't help but perceive it. X Rulo, this and this, and more tripods, no stars.
That's cool. Oops.
First cactus. Some I don't like as much. The dithers I don't like as much. But here's some fun ones. Peace roots. Starts with its peace symbol. Okay. And you notice that this is made of 5 white ones, and the white one is made of 5 black ones. So I had to Xerox this to 1/3 size and put it in here, and this to 1/3 size and put them in here. So these are
interesting,
interdependent. And I sometimes I had to make 4 at once. So start up with 4 and make the next stage for those 4, and the next stage for those 4. I dread to ever have to make 8 or 16 at once.
Well, and even keeping them, like once you cut them out, right? Once they were copied, once they were Xerox, you cut them out and then placed them. So, I mean, there was potential for error every time, man.
Absolutely. Absolutely. Oh, and some of them didn't come out okay. Some use the line, and I am absolutely certain that someone with a computer can make perfect ones, but I don't have those skills.
Kind of the hand things. I don't know. That's kind of the beauty of it. The computer, true. Yeah, you can.
That's true. I don't construct these things. I grow them.
Right. That's cool.
Here these, and yeah, you can see again. I was growing them. This one is these other ones were piece roots because they all branch out. You can see how it's branching out. Because each one of the piece symbols are splaying outwards, whereas here with these next ones, the piece symbols are inwards. So I call this one piece anchor.
Yeah.
And once I made one where this one it made me think that these look like like this one looked like Jean-Luc Picard, and this one looked like Francisco.
Right.
So Cisco bust piece roots, Picard bust piece roots, and here's Cisco bust piece anchor, Picard bust piece anchor, whatever. Oh, these ones, yes.
Those are cool. Yeah, look at that.
Whoops, sorry, that was an accident. This one I call Cisco Sus because it's kind of an S shape, but I also call it Cisco strip, and this one's Picard strip.
Nice.
And they're ones which are not based on discs, but are their own little thing. This one is chevron, made of 1, 2, 3, 4, 5, 6 in itself, and more of the same. And I put it in circle.
It remind me a lot of like the flower of life and sacred geometry and stuff like that.
Yeah. I mean, like I say, I find these meditative. Wait. There was one I gave to this one's this, and they get all gnarly. Let me see if I can find the arctrig. Oh, there's so many of these. I can lose track.
Gosh, look at them all. Yeah,
it's accumulated over the years.
Yeah,
what happens if you start to obsess on something? And oh, that's cute. They start off with a really rough looking sketch on a pencil sketch on a piece of paper, and then after I sketch them, let me see if I can find a.
The fat dragon looks cool.
Oh, here, this one.
Yeah.
Fat dragon. Here's how it starts. It starts with every line becomes a right angle.
Wow.
So it comes to here, then to here, then to here, then to here. Yeah. Let's see. Fat dragon.
Gosh.
Thin dragon. Some of these I neglected to record the way they were created, but let me find one of my favorites. There we go. Bullseye octagasket. Here's how it's made from an octahedron around an octahedron, and each one you replace and replace and replace. And I forget exactly what the ratios are that makes this work, but there they are. And I gave this once to a Buddhist monk in one of my classes. I figured it would be an adequate symbol of meditation. And
yeah, you can get lost in there.
That's exactly it. Yeah. So it's stuff. Or here's a more conventional one: octagasket, diagonal quadrigasket. Here's how it starts. Here's how it's formed. 4 squares in the diagonal, and you put the replace. Stuff. Huh. One of my recent ones that I kind of like. Well, hold on. I should show you one of the classics. I really do think it's a classic if I can find it. Just a moment. There we go. Octaves.
Yeah.
With 4 little yin yangs inside it. You see, and that's how. And there's a wave of highest formation, then one waving twice as fast, one twice as fast as that, and so on, going up the scale. This is it. This is in some ways a symbol of the real numbers in binary. So from a point here, it's 0.111011. So there's the right is the decimal point. But
ooh,
yeah, bullseye fire, bullseye water.
The bullseye water almost looks like one of those Japanese paintings.
Yeah. Horizon, fire, water, earth, of course.
Nice.
And here is just a second. Bullseye, horizon, bullseye, water, bullseye, fire, and earth, of course. But so that was octaves, but I'm actually pleased mathematically with, if I can find it. Yeah, this guy. Here were 4 I had to make it once, you see, because each one is sort of made of, well, actually, each one they come in 2 pairs. Okay. This one is made from this, and I think this. This one is made from this. And these also are a way of numbering lines, but it's a different numbering system, because with the octaves, you get an infinite number of things flip all at once. 0.100 equals 0.0111 for him. Here, at any point, at most 1 digit is flipping. So, so it's like a very alternate form of notating the numbers. And I ran into that because I was wondering about a mathematical question about, can you make a numbering system where only 1 digit flips at once at a time?
Right.
And it turns out you can. And here he is. You can see it. So that was fun. Let's see. And I don't know. I guess the starkness of it, the black and whiteness of it, it feels delicious somehow.
Yeah, you can see so much stuff in it. I feel like I see, rows of people standing. It's really wild.
Pareidolia. Here's someone I made very intimate orb. So
I like it.
I think it's very, very because you'll notice they're both seeing each other's noses, their own noses, and they're seeing the same thing from each other's point of view. So I think it's very intimate. And here's him, here's her, here's him, here's her, here's her, him, her, and so it alternates.
Oh, yeah, it alternates, doesn't it?
They're seeing from each other's point of view. You see, that's again adds to the intimacy. I think it's kind of erotic, actually.
Huh.
So, although everybody's fully clothed.
Absolutely. They had this need to be.
The labyrinth. From here,
Wow.
spiral all the way down to the singularity before you spiral out again. Here, from here to the corner.
That's really cool.
And okay, here to the corner and back again. This one, there's no way out. Here, it's much what you hear to the center, roundabout, to the center, roundabout, until you go back again. Horizon labyrinth. So you have to pass through the infinite horizon before you can pass out. This is the same thing, this much the same, this much. This is inverse horizon, inverse bullseye. This and this. This is 0.414 root 2 minus 1 size compared to this. So these two and this 0.414 squared can fit together. And the same, and the same. And this is and this, and this, and this.
Gosh, there's so many. They're so impressive. Oh my gosh.
They just kept coming. I just couldn't help doing them. Let me see if I can find. Oh, well, there's this one, the pentagasket, a star of stars.
Mm-hmm.
The famous snowflake curve, aka the Koch curve.
So was that one of the other snowflakes that you just took the perimeter of? Ish?
Ish. I mean, it starts out dip, 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 and then you put four of them together, and four of them together, and four of them together, and so on. And then I put three of those together to make the star.
Wow.
It was fun. There's no question about it. It was tons of fun.
It looks it for sure. And it's continuing to be.
Sometimes, like I say, some of these, I like the concept, but it was just not, I just couldn't do it quite as accurately as I'd like to do. Because it's kind of busy and it's kind of close to two-dimension, and that's when it starts to get hard to do. Ditto with this compass web, same deal. Double hexagram web. That was, I saw this in a math department, posted up on the wall. I said, wow. I had to figure out what was its generating subgraph. Finally figured it out. This is what you do. And this is composed of, here's one copy of itself. And then here's one copy of itself with a corner cut off, one with a corner cut off. I had to figure out that corner cutting off thing. And then you put, so you put itself and the surrounded by each 2/3 of it. And then as for this, you take four of those 6 of those things and put them around in a row. So this I didn't really generate at first by fractals. This is what I generated by fractals. And this I did just a one-step cut and paste.
Wow.
So it was, let's see what else was there. Yeah, radiance web form.
Sometimes the shapes between the shapes that all the fractals make is kind of the mesmerizing part, right?
Oh, yes.
Like that triangle, the one in the upper left there, that triangle, that void triangle is just, I don't know. That's the one that feels like it's moving or popping out at me. You know?
I see. I call this radiance web because if you look, you see it's sort of all based on this radiation symbol.
For sure, isn't it?
And so it was, and I call this sort of thing crunchy. You can't kind of slide up. You have to land on crunch. And there's a bumblebee. Here's this hexagon, and each line is turned into this hexagon in the middle.
It's amazing that one little shape is what makes the whole thing every time, you know.
Phi. The letter phi, and each line of it are replaced by the whole thing, right? And I go on and on and on until I get this. Then I put 6 of them around in a, that's so I call it phi eyes. I put 6 of them around in a circle.
Phi eye, I love it.
and you get this. Again, this is like that radiance. So this is not made fractally. It was made from 6 fractals pasted together. So that was the fun of that part. This one, again, I kind of like the concept, but as you can see, it's very difficult to make accurately. So
Right.
not so there's different levels of hex dice on each line you replace, and like I said, it's kind of hard to do exactly.
You can imagine.
Hex phi, real favorite of mine. So letter phi with a hexagon, and each line replaced with a hex phi, and so on until it fractalizes. 6 of them around. That's the big one, and then put 6 of them around, you get this thing. Whew.
Wow.
Yeah, I know. They surprise me. I mean, I go to them and I say, okay, surprise me, and they do it. So
very cool.
I plan to one day, someday, to well, my daughter tells me that I should make annotations. I mean, each one I should give it a little paragraph or two, giving its name and a little bit about it and so on. And that would make a complete art book. And I just haven't gotten around to it.
That's what I was thinking, an art book, like catalog the stuff. It's beautiful.
It's captivating. Like I say, I am discontent with the fact that it has a rigidity to it. It doesn't have the smoothness of natural nonsense. But okay, it'll do. Hex piece roots. Here it is with a hexagon. Here it is forming. It's only lately that I've gotten into documenting how they form. You see,
right? That story is really cool. Yeah.
Okay, here's a whole bunch of ones based on Seuss. Some are more successful than others, in my opinion. You can see these are all on a theme. Oh,
I really like that one. Yeah, that's cool.
Yeah, inverse bullseye swirly. This is one. It's bullseye. I don't think it's quite as successful, in my opinion. Here they're all the same size. I think this one's pretty good, actually. And here again, octaves. So I think this one again. This is really, chocolate almond.
There you go.
All right. Well, and here's Horizon. This is always sort of like a standard one, very square, in my opinion. But sure, why not? Bull's almond, bullseye horizons. 1/4, 1/2, 1/4. You saw the circles. And making them almonds somehow, it kind of works. So really,
yeah, it's crazy the depth you get as you go down in size. It feels to pop out of the page more to the eye.
And this one is a funny thing. Here's how it formed. You can see that it's swirly, but somehow when you get to the end, the swirl disappears. Implicit. It swirls till it ceases. I expected that. I was hoping it would be swirly to the very end, but it's sort of hints at swirl.
Right.
But not quite.
But yeah, you're right. The overall composition isn't, as spinny as you would expect.
Some of these are kind of spinny. Okay, now these are all the Seuss variants. Depends on how many have circles on them. This one is this is a whole bunch. It depends on how you arrange it. Things. I mean, for example, if you arrange them this way, you get this kind of Z pattern. If you arrange it a different way, you get a kind of a somewhat different one. And here's ZV's XVX is made of X's made of X's made of X's. A little bit unbalanced because it lacks one of the 6 circles, you see.
Right.
But that gives it a whole bunch of free possibilities. Just the thought. And of course, there are all sorts of things, right? Things that I didn't even bother to do because I knew it would come out kind of ugly and awkward. So I mean, here's Seuss. It's my favorite. I sort of like the basic one. So now you've seen.
Super cool.
Well, I think so. Well, I'm glad you appreciate it, and it tells me, listen, I got to get to the art book thing. It might sell. I don't know.
Yeah, absolutely. If nothing more.
There's done so many things over the years that I thought, okay, this is beautiful. Maybe I can sell it. Nah, but
I'll just keep it.
I just do it I do it because it's beautiful, which means that it wins and I lose. Of course, these are the
Or
early ones. This was one of the very first ones I made. Here it's a single point of fractal. Picture of itself. All right, ripple. Here, if you close your eye, if you cross your eyes, then this is black and this is white, and these turn black but white and white but black. So it's a stereogram of paradox color, which was the whole point of what I was doing. I was studying paradox, so I want to know want to know what it looked like. Here, the Xerox of a Xerox of a Xerox of a Xerox. It's part of the Xerox machine. It's not thematically that great, but it does tell you how it shows you the machine that it's made of. A set containing itself. One day, a mad meta poet with nothing to say wrote a mad meta poem that started one day. A mad meta poet with nothing to say wrote a mad meta poem. Sort of close where the words of the poet finally chose to bring his mad poem to some sort of close.
There you go.
That wasn't mine. That was Martin Gardner. But I cited on paper. Thus concluded the beginning of a meta poet's riddle, and the poet wrote a title for it, the meta poem's fiddle, then proceeded toward an ending, though the poet's mind was spinning, thus beginning the conclusion, thus concluded the beginning.
That's great.
That was fun.
And it emphasizes the picture as well.
And here's something I made for some friends of mine, Cybernetic Magazine. And I was visiting them in their office, and I said, hey, can I do this? So I went to their Xerox and started working on it, and an hour or so later there it was, and the guy looked at it, and he picked up the paper and looked down.
That's great. Life imitates art.
You notice the noses, of course. Noticed your nose?
Now I do.
Stuff. Like I say, once you get on, this one I call Eternity.
That's great.
It was fun. Each hour, it's the next hour, you see. And there's Horizon, and like I say, and all the rest. Most of these are at least two I've used. Each copy contains at least two. So you get a very gnarly, feathery kind of thing. This is fire, water, and onwards. Bullseye. And okay.
Well, thanks for sharing that. I appreciate it. That's awesome.
You're welcome. All right, then. Well, it's been real. It's been not just real, it's been virtual.
Yeah.
So, well, all right. I reviewed Inverse Trig. Next time I'll be doing what's next, stereo vision or some such. So, and you know the routine. If you work them out, then you can if you work these out, problem sets out, then excuse me, where did I put this? Huh. Wait a minute, I'm puzzled. Anyway, didn't I have anything else? Oh, right. Once you work these out, then attach them to your homework or your extra credit to an email and send them in the inbox, and I'll send you back your grade as soon as I could. Let's see now. Did I or did I not? Well, I'm pretty sure I opened up everything, right?
I believe so.
Let me double check. Quiz 2. Yeah, and the final. So everything's available.
Yeah, I should have the final too, probably tomorrow.
Hey, when you're ready. When it's full, we have like a month left too.
Yeah, I got plenty of time.
You've got plenty of time. So yeah, and then plenty of time to consult with me. I'll be here on Mondays. I'm sorry. Yeah, on Mondays and Wednesdays at this time. And I might show some more fractals. And,
nice.
All right, it's been real. So if you have questions, please ask, or we'll end it off. Motion to adjourn.
Seconded.
All right. See you later. Bye.
Thank you.
Bye. Thank you.